Work. All right. Oh, it is recording. All right, so the second lecture is there'll be two blocks in it. We'll see how far we get. The first block is more of the how you read a paper, and the second one is how you maybe write a paper a little bit better. Some of the ideas, what you could add to your paper, what you could share, sharing data, etc. And I want to start with a recap of what we covered last time. So my thesis is that you can't really tell most papers how legitimate they are because it's essentially an essay. It's a text, several pages of text with some figures. And I gave you this example from my own career where if I made figure 4 into figure 1, it would be a completely different paper claiming something amazing. And then because we did find that this wasn't something amazing like spin polarization at zero field, we put it at the end of the paper with a little explanation, and it became a different paper. But it's completely up to me. If I do it differently, then chances are the paper would have been accepted in a different form, and maybe later it would be debunked or maybe just forgotten. And this is how all of it goes. And then what I was trying to develop last time is how elaborate it could be that a paper looks very convincing and it could even be correct, but nevertheless there could be an alternative explanation, or sometimes it's very easy to find that the paper is wrong, and yet nevertheless it could have been accepted and published and so on. And so you shouldn't go by which journal it's published in, perhaps, but maybe think for yourself. And for the postdocs, it's already probably more obvious. So it's more message geared for starting graduate students. And then I did flash this slide, but didn't go into detail into this. I shared it with you guys. But this is about how I read the paper, and maybe this is helpful, and maybe you can propose some other ways. But data and data presentation, amount of data is probably 70% of all of this. So you can look at the figures, and I'll show you some examples where the data range could be weird, like too narrow. They only showing a small segment where it's, that they probably looked at a wider range, but they're showing a small range, or maybe the scaling is weird, or the colors that you cannot see something. If you feel like you want to see more, that's this part. Now we also talked about, we didn't talk much about this. We'll talk about this maybe more today, but some of these points are about, the data just reads too perfect. There are no problems. Everything's good. They did not encounter any issues. There's no rough edges, no alternatives, no imperfections in the data. So a lot of these points speak to that. Like, for instance, is it too good to be true? You can hear that phrase used often when people are doubting, but they don't have they cannot present you with a reason. They say, okay, it just feels too good to be true. They don't say why necessarily. Maybe they don't have evidence what's wrong, but they would say this. And this is sort of in essence a catch-all. So maybe, the physics is reasonable. There is no obvious mistake. The data shown looks good, convincing. There is no obvious alternative explanation that you can think of, but still, it's just too too good. Something like, I don't know, suddenly we have Majorana fermions. Oh, amazing, right? We are happy, we found them, but maybe it's just a little too soon, a little too good, right? The theory was a few years ago, and suddenly we have this effect. So this is just an example of something that you may not know what could be specifically wrong with it, but it just feels too good. We talked about alternative explanations extensively last week, and we talked about this where from experience, you can draw from your own experience or your colleagues, your advisors, that they've seen something like this 10 years ago, and they know that could be a different explanation there. And this is a slide that is partially a joke, but the point I'm trying to make here is that, well, a paper that's ultimately unreliable, it does try to trick you in some way. It does try to trick you, convince you that it's right. And like I said last time, we leave outside the brackets the question of whether it's a matter of the state of mind. They are trying to trick you, or they're tricking themselves. Not important, but somebody is getting convinced by this paper, and it's often broken into a set of arguments. And so here I just mapped onto the stages of a con. And so the confidence trick, where they are, for instance, they're telling you about a great enterprise that you have to invest in, and they put their own money, and then something goes sour, and they disappear with your money, and that's a confidence trick. And interestingly, there are a lot of similarities. So, for instance, oftentimes there is a previous paper that maybe did not make the big claim, but came close to it, or said, okay, because our sample was bad, we failed to achieve something amazing, some topological state, or from your field, some example, single photon emission or whatnot. Then there is some kind of an advance presented, like, oh, now we achieve better samples, which could be true or not. Maybe that's just one good sample, or not even a good sample, but we don't know. But it's just, you can just recognize this pattern. Okay, so we made a leap forward, and then there is often some simple measurement. Like, for instance, we talked about Shapiro steps last time. I know I lost all my audience with this, but Shapiro steps, I told you, it's an uncontroversial, robust measurement that's known for decades, and they will present you a beautiful pattern of Shapiro steps that are just no missing steps, no extra steps, just something good. So to convince you, okay, this is a junction, Josephson junction, that shows Shapiro steps as you expect. And it sort of draws you into this paper. Okay, you're following along, right? This makes sense to me. I've seen this before, simple effect. And then, bam, comes something that blows you away, right? And then before you have some dramatic pattern like missing Shapiro steps, before you have time to orient, maybe they try to distract you. They give you something weird about it. Like, for instance, oh, it only happens at low frequency, or your zero bias peak is 5% of the desired height, which is an example from my own paper, which is, was reliably reported, the data, but it was later proven to be wrong by others and by ourselves. And then a lot of people focus on this feature. The theorists go crazy. Why is this peak not quantized? Why is it so low? Oh, let's write a theory that explains it. And so they're completely drawn in a different direction. And then finally, something confirming. But yeah, we did a check, we did a sanity check, we measured another thing, or we did it in another device. So this scheme with variations, or maybe some of the steps will be present, but or maybe it's you might not recognize all the steps when you read it. But I just want you to have in mind this picture because there's got to be some convincing in the paper. And this is for obviously unreliable papers, right? It's not for papers that honestly trying to report something, trying to be comprehensive, and then later proven wrong or alternative explanation found. This is this kind of more directly unreliable. And so this is an example of my work with my colleagues and friends where we got these two papers retracted from Nature. And I realized last time that a lot of you guys didn't know about this material, but I'm not going to go too deep into this, but I just want to illustrate that there's actually two papers in Nature. The first one on the left got retracted second, but they two work together in a sense that the first one reports advances in creation of samples. You know, we make better materials, better materials. And then in these materials that are already reported in this paper, we find some amazing phenomenon. Right? So by the time you read this paper or you receive it as a referee, you already know that, well, these are, in fact, I think the opinion article wrote something like heroic samples. So these are amazing samples. You know, this paper makes it, the one on the left says that these are suitable for quantum computing. You know, they're good enough so you can build working devices out of them, right? And then, of course, it's less of a leap, less of a problem. And so this works as two separate papers that are two of the stages of the confidence trick. They can play. And I told you it's 70% data, maybe more, but let's be conservative. It's a lot of it is about how data is shown, which data are presented. And so what I encounter a lot in our community, and maybe beyond, is when people say, well, you got to trust the data. You can't argue with the data. You can argue about what it means. And does that seem reasonable? I wrote wrong on this slide, so I guess you are not encouraged to say yes to me back. But yes, especially senior colleagues, they think like this. Theorists certainly think like this, right? If you see an experimental piece, they say, well, who am I to criticize the experiment? I don't know anything about this, so I can just look at the plot and I can create a model to interpret it. This is what a theorist would say, and perhaps they should. Get a little bit of experimental training and train to sort of read the data a little bit more. But I will show you some examples where nothing was done with the data, but nevertheless the paper is unreliable. And I also show you examples maybe a little bit where data were actually manipulated. But they are equivalent, right? So because ultimately, they all lead to the same point where the claim that the paper makes cannot be trusted. Whether a data set was completely made up, never obtained with a piece of equipment, was made from the brain, whether it's been manipulated, like something done to it, some data points moved, etc., or whether it just contradicts the rest of the data. Still unreliable. So here are some examples of non-representative data selections. One is, this is an SEM picture of a growth of nanowires. So the wires grow vertical out of the substrate. They are single crystals. They're nice. And of course, what you want is for all of them to be perfectly straight, uniform, long, perhaps other things you care about, but you often show a picture, like a scanning electron microscope picture like this. But what you see in the background here, if you look in the dark, that this specific growth, and I asked for this picture, right? I asked my collaborators to give me an unsuccessful growth, right? So this is actually a relatively poor growth, but some wires look good, but others, they're tilted and twisted and deformed, and there are some non-wire things on the substrate as well. And Well, if you say it is possible in principle to grow wires like this, but the yield is low and there are also other things on the substrate, that's okay to present in a paper, right? But if you say we achieved this robust, reliable growth, that's a problem. Here's another example. So it's from one of the retracted papers where the paper is about quantized Majorana conductance. So what it means, quantized, it means that some signal conductance at 0 voltage here, the middle line shown here, it reaches this value of 1 in units of 2e²/h, which is called quantized, and it kind of stays there for a range of parameters. So this is a claim from the paper. This is the figure. Happens right here and right here. The problem is we've seen something like 25 different data sets that all look similar to this, but only 2 of them have this value. Right? So this is all the data that we obtained from this group, and you can see the overall pattern looks like this. There is these merging resonances, or sorry, this way, merging this way, and where they meet at the meeting point, the conductances can be 0.5 of the quantized value, and in some instances is 1.5 of the quantized value. And so there is no systematics here. You just pick the one that is of the right value, and you say we've achieved quantized conductance, right? But there is no scientific process here other than declaring that the value you're looking for is the right one. A self-fulfilling prophecy, essentially.
They didn't have anything in their supplemental information, like extra devices and these?
They did have, so this was quite elaborate, right? They reported several devices. They said they had even more studied, and they also reported non-Majorana things in one of the figures. But the point is they didn't have anything in any of the devices. And so here is another example from that paper where this is about the range as much as selection. They showed the orange trace in the paper. And then we obtained the full data set, and it's orange plus the blue. And this is, again, this conductance at 0 bias, the same signal as I showed you in the previous slide. And you can see that the range they showed is sort of 350 to 4 something, so about half a volt on this gate. And if you're working with these devices, you might say, well, why does it start at 350? Why does it end at 415 or so? Didn't they study from -3 to -5 or something logical like this? Or just what do I see here? For instance, it kind of looks like it goes above this red line. And of course, the red line is 1, the quantization line. And the line in the paper, the text that accompanies this figure, says that the signal, ZBP height, comes back up to the quantized value and does not cross through it. So there's a direct contradiction. It actually crosses through it right at the where it was cut. It crosses through it, and it goes up to about 1.5 gradually. And there is no reason to just show this piece without showing the rest. Right? So this is about the range and about data emission. And this is not just selecting the best. Right? Like I picked the best nanowire and didn't show you the worst nanowires. This is full data directly contradicting what's written in the paper, right? So by choosing, but these data, the orange data, are not manipulated. They're just reduced. There's no manipulation. They also done manipulation in that paper. Now, yeah.
Did manipulate data?
They also did manipulate data, but my point here is that that's even a less important problem than what I'm showing you. Right? So there is another type of bias that can happen that is much harder to detect because it happens in real time as you're taking data. You might see, it's not going in the direction that I like, and change the parameters actively while you're measuring in a different direction. And that's very difficult to detect. Of course, if you obtain the full experimental log, the journal, and the data, you might see it. And in one instance, we did see it. So this is the other retracted paper, and the figure is on the left here. The point the figure is making is that it's a beautiful, featureless regime. Featureless meaning there is one feature. There is this stripe of low current, which is called the superconducting gap. And it just evolves gradually, very smoothly from lower current to higher current as they go from left to right in this panel. And this is used as evidence of very good device quality, right? Suitable for quantum computing, etc. And then we obtained some data where we see that, you see this is, again, the range is -6 to -4. So you may wonder, well, did they measure from 0, right? Because it's easy to start the parameter of some voltage at 0 and sweep to -4 and then go to -6. So they must have data from 0, right? So yes, they do have data from 0. So this is this upper left. You see the horizontal axis starts from 0. And around 0, there are very dramatic features, these stripes, red stripes that crisscross through. And they are very much undesired. They are actually evidence of that the device is not so clean and not so uniform. They are signatures of, in fact, quantum dots. And here is, so here it looks like tried to adjust the range to -0.5 in the lower left. It still got one of these resonances in there. So then adjust it further to -3 and -0.4, try to retake and got a few scans that don't have them. And then actually here the manipulation came, because then they removed some of the lines randomly from here, the ones that didn't look so pretty, and then combined these two panels. And that's what you see here on the left. So this figure is both selected and fabricated and selected in real time. But we kept a trace of what was happening in this device. So this one is much harder to detect, but it can also happen, right? So good to be aware also for yourself. You take data, take it in a comprehensive way. Right, so this is still on the analysis side, how we read the paper and what might we see that could be a signal, like, oh, pay attention, watch out. So we'll talk about some of these things, but they are very common in our field in condensed matter. In fact, the first one, model agrees with experiment, is almost a requirement for some journals. If you don't have a theoretical analysis attached to your data, it's seen as less valuable, might not get accepted in a journal like Physical Review Letters, for example. So this is very much encouraged. And then, of course, if the model does not agree with experiment, the referee or the editor might say, oh, go back and do more work until you understand what's going on, right? So there is a huge force in our community towards this agreement, right? And therefore, oftentimes, this agreement is beautiful. Model does agree with experiment. Another one which is very interesting, you heard the expression smoking gun evidence in this context, right? So I define it as, and we will talk about it a little more, as a single data plot that proves it all. Right? From one figure, you can see everything. And then the rest is just sort of due diligence. Yeah, okay, we are good experimentalists, so we looked at this and this and this, but here really you can see it, right? And of course there are examples of such experiments where from one figure, from one trace, you can just completely see and the effect and be fully convinced, right? And because there are such examples, because they exist, then we all want to live up to that, and we all want to find a data set that is a sort of a bullet, a smoking gun, a proof. Right? So there is a huge push for us to do it, and so you may find it in more papers than where it deserves it. Right? So, for instance, the pattern of missing Shapiro steps would be a smoking gun for fractional Josephson effect, which is a strong evidence of Majorana fermions in topological junctions. And so you show this one plot and you don't need to show anything else. Or maybe you do. Okay, then these confirmations from several measurements, right? It's something that a referee might ask, well, what about the temperature dependence? You're measuring in a dilution fridge at low temperature, and they say, well, have you tried to warm it up and see consistency? So, and then you say, oh, yes, we did it. And they say, okay, well, I guess it's correct then. Right. So this you can also see. And then the one-liner effect is when you say, well, your hypothesis is not possible because this effect is 100 times less weaker than what we are reporting here. Right? So a one-liner rule out. Right? So not nuanced, not detailed discussion, but say other effects are just impossible, fundamentally impossible. Or what else could it be? Right? So it's related to smoking gun, but slightly different. So so these are the things not which, the paper is tricking somebody, right? Like I said, again, it could be tricking the author themselves, or it could be tricking the reader, or both. Everything is possible. But these are the thinking patterns that we often use, and occasionally they're justified. But in most cases, we can do better than this. So speaking of the smoking gun, right? So one plot that proves it all. I already talked about the middle panel here last time. So the missing Shapiro steps, the red arrows indicate where they're missing at 1, 3, and 5. And these are histograms, remember? So these are sort of the data points are, the signal strength is how many points are at each voltage. So when there is a step or a plateau, there is a concentration of points and there's dips. And if you remember from last time, then I'll remind you that this is our data from my group in a non-topological regime where we don't expect fractional Josephson effect, but we just fine-tuned our data to have these Shapiro steps missing. And so this smoking gun evidence, but it actually does not correspond to anything interesting. And likewise on the left, it's another example of zero bias peak. So there is a paper that shows this kind of plot, and the signal is at 1, within 5% of 1, and then they say that, well, this is significant. And now in my group, we have a signal that's 0.5. We also have 1.5, again, in the same spirit as I just showed you, this one smoking gun panel. This one is, you have to look at these lines as they go, and then they shift, and then they shift again, and there's multiple lines that do these shifts, and the shifts form their own lines. So something like this, a little bit different, but was reported as evidence of something exotic called braiding. So when you have exotic particles called anyons and they move around each other and they interfere non-trivially, and the shift, the fact that the shift is not by 1, like the lines perfectly stitch again, but they shift like this, means that they have exotic charge like 1/3. So this would happen in a fractional quantum Hall effect, where we have these predicted, and there's a lot of evidence that they're 1/3 quasi-particles, but there's not been quite this interference effect demonstrated until recently. But this data is from my group, and this is from a little quantum dot, not in the fractional quantum Hall regime, or not in any quantum Hall regime, in fact, at 0 field, I believe. And there is another charge jumping nearby. And when that jump happens, the entire pattern shifts in the main dot through which we send current. And so these are charge jumps. And I just found an example where they line up in lines like this, and they are a fraction. And this fraction is determined by capacitive coupling between the side dot and the main dot. So if the dot is very far, the shift will be very small. If it's right on top of each other, it will be by 1. And if they're a little bit decoupled, it could be 1/3 or 1/4 or 1/2 or any value you like. And this happens, these kind of charge jumps happen quite often. This is actually quite remarkable because mesoscopic physics at least, but I'm pretty sure other fields of science as well, are so rich. The features are so elaborate. The patterns are so striking, right? All these colors, all these stripes and peaks and Shapiro steps and things like that, squid patterns, are so striking, yet they can be obtained in more than one way. So the smoking gun, if you're looking for the smoking gun, you have to be aware of it, that there might be another way to get to the smoking gun. So for instance, zero bias peak, there are multiple possibilities for it, why it would occur. And one of them is the sought after possibility, and others are less sought after. Could still be interesting, but there's just multiple possibilities. And this is not obvious, right? So when a theorist writes down a model and they say, well, I have this dramatic feature, what else could it be, right? This would be the smoking gun. But there could be multiple ways to get it. Yeah, this is just my little joke on this data. The smoke is also undergoing some kind of non-abelian phenomenon. I tried to make it something like one. Theory and experiment. Okay, so I introduced to you a pair of papers. It's actually a remarkable story here because both are in Science magazine, and this one on the left is earlier, and the one on the right is later. They used the same material, I think, literally from the same chip, but at least from the same kind. It's a nanowire again. It's my field. I give you examples from my field, and it's clad in a shell of aluminum that is completely covering the wire. So it's full shell nanowire. Right? So we have full shell nanowire on the right and a full shell nanowire on the left, and it's literally the same wire. And the paper on the left says that they've observed something topological. Even nature label or science, labels as a topological matter. That's the category. And the paper on the right says, well, it's non-topological. Okay. And the data are similar. You know, whenever you make experiments like this, you can imagine that the features are so rich, and it also means that any little difference in the two samples will make them slightly different. But qualitatively, you have these kind of oscillations, darker oscillations on the left, and you have some kind of darker oscillations on the right. And inside the oscillations, there are some bright resonances. So here on the left, there is this peak. And here on the right, there's also situations where in the second lobe, there is peaks or they split and so on. So, well, the paper on the left actually happens to be under editorial expression of concern, which is also work of my team, where we found a little bit more data, and we concluded that this is not representative of the rest of the data. It's basically just fine-tuned to the situation and nothing special about it. And the paper essentially claims the coincidence of this resonance inside the second lobe and the lobe itself, right? And then in practice, you can have all kinds of situations. But what I want to draw attention to here is that both papers come with theory. Both come with models, and there are theory co-authors on both papers. They're different people. But in both cases, theory agrees with experiment, and of course with the interpretation. So on the left, theory, on the bottom left, agrees with experiment and confirms that this is topological. On the right, the bottom row is theory, and it agrees with data and says it's not topological. So this is just to illustrate that any claim you want to make, you can find a model that will fit your claim, right, and reproduce your data. It's possible, right? It's not possible in every situation, but it is possible more often than people think, right? And even dramatic features like all these beautiful, colorful resonances and lobes and oscillations and so on. So what I want to say here is that, well, if you do show a model, try to present it in a way where we can see where they diverge, for instance, right? So say, the model gives us this, and the samples have this, and maybe there are some similarities, but don't try to perfectly fit the two, right? Present it as okay, within this model, we obtain some of the features. So that's what I'm trying to do in my group, explain to my graduate students that we need not chase the perfect match between the model and experiment, right? We just to make some assumptions, and always keep in mind that whatever you put in your model is probably not what is in your sample, or not completely. I showed you last time that some of the alternative explanations come from additional considerations about the sample, something like it's inhomogeneous, right? And it can give rise to similar phenomena as something exotic you're after, right? There are some extra impurities, extra states that you're not thinking about. So what is in your Hamiltonian is not necessarily what's in your sample, right? Whether you start from the Hamiltonian or whether you add it later, once you already have the data, in both situations, it's like that. Okay, so at this point, people say, and I also sympathize with this, well, if we are so critical, we don't allow the smoking gun, we don't allow the confident claim, we're gonna throw the baby with the water. We're gonna suppress debate. It's a way of doing science. You see something, you think it could be something interesting, you share it with people, and later maybe it'll get sorted out. And maybe somebody discovers, what this picture is, right? It's a flux capacitor from Back to the Future, and the doc showing the picture. So maybe we throw out a major discovery like time travel or warp drive, or indeed might run of fermions, because we were too critical, too tight, too strict. Actually, in this case, we did allow ourselves to. So here's a theoretical paper that we wrote about a braiding device, and we did say in the paper that it is flux capacitor shaped. But of course, it was not a real time travel device. Google now made one for real.
Right, in nature.
The wormhole device. So, right. So, well, it's a legitimate point, and you don't have to. You can take it from the source essentially. So this is a report that's already been made quite a number of years ago for Physical Review Letters, which is one of our biggest journals, and the recommendation of this committee that included some of the top physicists at the time says that essentially the journal is not publishing enough of the speculative papers, because those are the papers that push the science forward. Right? And maybe that was true at the time. Maybe the referees were too harsh. Maybe that in that reality, although I'm not so sure that was the case, but there was a big scandal of Bell Labs when a lot of papers got retracted about 20 years ago. And maybe right after that, the referees were very harsh on everything. So I guess, I don't know what you think about this. My point of view is that everything's good in moderation. Right? So we can be hopeful, but we also have to, we still have to be careful. And so if every graduate student thinks they discovered a new state of matter, probably a lot of those states of matter are not real. Right? So I wrote this little opinion piece, essentially to urge a little bit more caution. And if you like, you can check it out. Because to basically counter this point, right? Yes, we can be hopeful, but we cannot be hopeful all the time for every little artifact in our data. By the way, I don't know why, but it was based on a real picture, but somehow they replaced Bo Min with a female student. I think this is also a fine picture, but okay. So one of the diagrams I had in this opinion is this diagram where I put different topological phases based on this phase diagram. In condensed matter, we really like phase diagrams, and this is a very qualitative one, but I think there is some truth to it, some accuracy to it, let's say. And the point is that if you have a large energy scale associated with the new state of matter that you're discovering, then it's easier to see it, of course, right? Not controversial. If it can be seen at room temperature, it's easier to see. So room temperature is right about here at the top. And then also if it's very clean, not disordered, which is here is mean free path, so disorder increases along the horizontal axis. If there is low disorder, so in the lower left corner or in the left corner, it's easier to see because there's less variations, less averaging, less disorder. So interacting topological superconductors, forget about it. You will never see it. The energy scale is so low predicted, and disorder is probably high because you have to combine 3 or 4 different materials and rely on different effects that have not been demonstrated. On the other hand, the integer quantum Hall effect, very reliable. We can believe that. It's kind of like Shapiro steps. Well demonstrated. And graphene can be seen at room temperature. And then, of course, there's this line in between, the fog of hope. So it's a fog in both senses, where it's a fog because it's hard to see clearly because there's all these alternative explanations and imperfections. So the signal you're looking at could be it, or could be something else. And at the same time, it can fog you. The hope can fog your brain. And you can think, oh, I'm really seeing it. I'm really seeing it. And maybe that's not the case. Okay, so that was the first block. I don't know if you guys have any opinions or thoughts at this point. Otherwise, I move on to it with some of the, I don't want to say best practices, but some of the attempts we're making in my group to write papers in a slightly different way. So it's a little bit more work, but I think maybe you can tell me what you think about these ideas. Yeah, go ahead.
What happened to the group that fabricated their data? Like, what is the punishment, if any, that happens to people that do this?
Right. So I did want to leave it a little bit out of the discussion, the actual misconduct, but I'm happy to answer the question. So different things happen to different people. Some are still professors. Some moved on to different jobs. Some papers got retracted, but I think they got new papers accepted to very good journals since. And there's been some investigations. It's a messy business. I could give a separate discussion on just the how our system processes these kind of situations. And the short resume is not in a good way. Yeah, we don't have a very good way of dealing with it. And some of it is justified because you don't want to end someone's career based on unsubstantiated accusations, for instance, right? So some of it is justified, but some of it is basically the system trying to protect itself, avoid scandal, suppress these kind of things.
We have seen a pattern from these groups, right? That they have this a lot of these papers, right?
Yeah, we found multiple papers.
Right. I don't want to name them, but is it legit? I know you use that word in the title. Is it legit to avoid papers from these groups, or totally?
Yeah. So the question is it legitimate? Should we just ignore some papers? I would say so. Some people might disagree. So say we should take each paper at face value, and also these groups published a lot of good works in the past, at least on different topics. But the reason I decided to put together this material, one of the reasons is because my students kept asking me or keep showing me these papers, right? And I kept saying, oh, ignore them, right? And at some point, there were so many papers to ignore you basically start, basically you give advice to ignore the whole field. But we need some kind of reference foundation, some discussion. Graduate students need something to read, something to learn from, and so this is when we started asking for data and things like that, and getting to the bottom of it. So if you ignore it, it will grow. That's what I'm trying to say, right? So at some point, it reaches a critical mass where you can't ignore it anymore. You have to either you just quit, fold, do something else, or you have to do something about it. And in some of the areas, we are at that stage for sure, but I think also the wider physics or condensed matter physics situation could be a lot worse than we realize. So I would say we should not ignore. We should go beyond ignoring. We should do something. Okay, so how we write papers. Again, I said it's 70% about data, and just simply putting more data in your papers is one single best thing you can do for your paper. And in fact, it's gonna become more and more required. For instance, this is a letter from the director of OSTP, Dr. Nelson, and she writes about several things here, about access to research, essentially, that is federally funded, and it's all reasonable stuff, but it is a culture change, because in the past we had paywalls and we didn't share much data, and she's basically saying that starting at a certain moment, December 31st, 2025, you have to share all your data. Right? So you might as well get ahead of it and start sharing more data, think of how you will share it. And fortunately, it's not so hard. For instance, my group puts essentially all our data on Zenodo. So for each published paper, the entire body of work. So let's say we show data from one sample or two samples, but we studied 10 samples. So we just put everything. Zenodo gives you 50 gigabytes, and you can just, for many experiments, dump everything there. And okay, it's better if it's organized, it's more useful. But even just as a backup accounting, even for yourself, for your mind, that all that I did is out there. It might just already precipitate a better paper out of you, just because it's out there. And yes, you can do a better job organizing it later, as we develop more tools to, but of course take better journals as you take experiments, make better journals and keep records better. Just because you know that it's all going online, my students started keeping records a little bit better. And yes, for some experiments, it's too much data. Some synchrotron experiment might generate gigabytes and gigabytes of data, or density functional theory calculation might be terabytes of data, and you wouldn't put it all there. But you can still put more. You can put scripts online. You can explain how you process your data, how you truncate it and shrink it to how we obtained the figure. What was the path that you took? So you can do these things, and this is a single most impactful thing. That's improvement for your paper, and oftentimes you read this kind of thing, data available upon reasonable request. And I just basically argue that this is a very harmful phrase, because on the one hand, you're trying to be open, and when you write the paper, maybe you put this phrase there because it's just something that's always at the end of the paper. Or maybe you sincerely believe it, that if somebody asks you for data, you will share it. But chances are, if somebody asks you for data, you will not share it. Maybe you moved on and graduated and forgot the hard disk in the old lab. Maybe the person that's asking for data is coming on a little bit aggressively, like, oh, I don't trust you. Can you show me what you did? Right? And you just feel like you don't like them. And then you feel like that's not a reasonable request, even though it is perfectly reasonable. So chances are you will. So this is basically a code word for we will not share data. That's what it means. So just share it. Don't write this sentence. Just share the data. Then this is as much about writing a paper as about how you do the experiment. But even if you just think about that essay that you're writing, that paper, that 4-page essay, you put in these elements that explain where the rough edges begin in your work, right? So remember I told you that if I read a paper that sounds everything is perfect, everything is beautiful, everything fits perfect to the model, I am suspicious automatically because I know that something was not perfect and I want to know what that is. So just explain what that is. Maybe that's a minor thing and there's no concern. Or maybe it is worth thinking about, but you have good arguments why your hypothesis still works. And that makes it okay, right? We can still accept your paper and discuss it as scientists, and maybe it's proven wrong later, but so be it. That's how science should work, right? So then there's two types of research, as you all know, I'm sure. One is hypothesis driven, is for instance, if there's a theory paper out there and you're trying to implement what they say. So Majorana is an example of that, right? There was a theory paper from guys that are now at Microsoft, and we tried to exactly implement that Hamiltonian in a nanowire. And then there's exploratory. So we synthesized a new crystal and let's shoot X-rays on it. Let's send it to the synchrotron. Let's put neutrons on it. Let's do transport and see what we find. And then we find some artifacts, and because it's a new material, oh, it's got to be something interesting, but it could also be something like thermoelectric effect, something boring, but it cannot be because one-liner explanation, it's hundreds of orders of magnitude lower. And yeah, so explain what the concerns are that you thought about. Just put them in the paper. Yeah? Maybe you discuss it in your group with your advisor, but you leave it out. But you could also just put it in the paper. So here's an example where, again, using Majorana research as an example, I put together these 5 criteria for what would constitute a Majorana demonstration with these nanowires, with zero bias peaks, with these things that I've been working on. And it's not important what they are, and maybe some people would disagree with these 5. They have their own set, their own criteria. I'm just using it as an example here that, okay, maybe we went past step 1 and past step 2 and past step 3 and past step 4, but we failed at step 5. Then I can explain that using the hypothesis, this hypothesis-driven research, right, that this Hamiltonian leads to these 5 things, we've gotten to number 4, and then at number 5 we encountered problems, and the problems could be due to A, B, C, D. Right? So I found where, at which point the hypothesis fails. And maybe, just maybe, the first 4 are already looking pretty convincing or interesting for people to discuss. And also the reason why the 5th fails is not fatal for Majorana, but it just requires more work, maybe cleaner samples. Right? So we are having a normal discussion where I disclose at which point where we are hit the wall in my paper, right? And this seems reasonable when I present it like this, but it could be actually scary or discouraged to put this in the paper, because you might worry that, well, the referee will pick up on the weakness of my paper and downgrade it or reject it and so on. But this is a good way of doing things, right? Again, you don't have to prove it 100%. If we relax this requirement, our life gets easier. So here's an example, one of our papers. We wrote a theory paper that predicted Andreev blockade, doesn't matter what it is, and then we tried to find it in experiment ourselves. And the effect is basically that there should be a bright line of signal followed by a dim line, then bright line, then dim line, then bright line. And then if you change the voltage direction, the bright and the dim line should trade. So what was dim becomes bright, what was bright becomes dim. And so we've obtained all these data, and it kind of works. So we decided to write a paper, but also it didn't work perfectly. So for instance, in the lower left corner, if you focus on this part, it kind of deviates, right? And so we wrote up where we think it deviates. So we consider some possibility that this whole effect is identified due to fine-tuning in search for predicted patterns, right? And then we say, well, this is how it would occur. We cannot fully exclude the possibility, and we say we see in Figure 4, lower left part, that there is some deviation from what we expect. And then we say, well, we still think that on the total of the evidence, not smoking gun, but from all the data, we still think that this is likely what we were looking for, but we cannot exclude. And so we wrote a whole half a page about this. Okay. So this is an example of pushing a hypothesis to where it breaks and explaining that point. So this is in lieu of a one-liner, right? I could have said, oh yeah, it's not that. Oftentimes, it's also very natural for people to look for a metric, like, oh, I want to find something very simple, like high mobility in my sample, and describe my entire experiment with one number, right? Just like many things in life, your grade, your impact factor, it's very attractive to have one metric. And oftentimes science is more complicated than that. So it requires multi-factor approach analysis. And so, for instance, what I show here in a picture is from one of our papers. The sample was actually produced at UCSB here. And it was a very good sample, gave us many different interesting effects that we studied, and we wrote several papers on it. But also we found these red and yellow arrows are denoting the sizes of the grains. Right? So we could have said that it has hard gap, and some of the other impressive things from this list. But we also disclosed in our paper that it is not a perfect crystal. It has grains. It's a polycrystalline sample. And nevertheless, the paper was well received and so on. So you give a full picture, you give a multi-factor assessment, and it's still okay. So not related to necessarily reproducibility and discussions like this, but I put together for my students a way of breaking up paper in little chunks, and you can look it up. You may find it useful how I break it into chunks for writing paper. But relevant to this discussion is we try to add these specific blocks to our papers, and we already talked about a little bit about alternative explanations. Duration and volume of study is a very simple thing to write and could be very helpful. For instance, did you measure for 1 week or for half a year? Both could be fine. There is no wrong answer here, right? But it gives, at least to the specialist, to the referee, some idea how long the measurement should take versus how long it took, how many samples, how many data sets you obtained. Right? So for instance, you're showing 30, but you've obtained 5,000. Right? So then there could be a question, well, how did you choose the 30 for the paper? Did you choose it well, representative, or do we need to see more? Or maybe you're showing 5 and you've obtained 5. Okay. No questions. Data availability, not upon request, but putting a link to Zenodo where it is, and I'll show you some of the other examples here, study design, etc. So here are some alternative explanation blocks from our actual papers. And the point I'm making here again is that these are not one line, although some are hand-waving discussions, like for instance, these self-field effects are ruled out in this case by order of magnitude. So that's also, to a physicist, that's okay, that's legitimate. Some are pretty long. And you could also just make it a habit of writing this block for every paper, even if there's no alternative explanations. You can say alternative explanations were not identified. And but you get in the habit of thinking about them. What was there anything to disclose here or not, right? These are some of the data availability, duration, volume of studies. So just to give you some examples, for instance, what do we have here? 20 chips were fabricated, average 7 devices, 50% not resulting in any data. The first chip contains devices 1, 3, and 4. The second chip, device 2, etc. Was done over 1.5 years. Here, started May 2021, ended May 2022. Some more time, this many devices, 5,200 data sets. So this is what you write, and I think this is a very simple change that already increases the value of the paper by quite a bit. This is more exploratory. We've played with this. I'm not sure how useful it is, but there is a big discussion in the reproducibility arena about pre-registering your protocol for your study. So you first publish, I'm going to do the experiment this way, and then you do it exactly that way, so that you sort of confine yourself, what your hypothesis was, what you're looking for. With exploratory research, it's not always possible, right? But what it's trying to prevent is, it's called harking, I think. I don't remember what it stands for, but the meaning is that you, on the fly, change what the success is based on what you measured, not based on what you were trying to find. And maybe that's not such a big issue in our field, but it could still be helpful to lay out for people with some of the details what the different stages were, how you process data, how you selected data, what were the principles, so you can fill some of these things. And we don't do it consistently ourselves, so this is something I'm not sure how useful this is, but it could be useful. And finally, I see pizza is here, so we'll wrap it up a little quicker than last time. You may hear these words, open science, and what this means to me is that you have to do something extra, really go out of your way to participate in this process. Submit in different journals, do extra things. But what I want for you, your future to be, and my own future, however much left in my career, is to redefine this way, so that this is the default. We share results, we discuss them openly, we don't worry about the crazy things like the referee will not appreciate my openness, etc. And this is really close science, because this is all the things I don't like. We didn't talk about all of them, but I think all of these things are, of course, behind what leads to a lot of the unreliable papers of the foundation. I just decided to leave it out of this course, but you probably seen some of these things. So let's stop here. Thanks so much for coming. I appreciate it very much. And if you have any thoughts and ideas, I'm happy to keep talking, or maybe let's grab some pizza.
Smallwood is vegan.
Perfect. Thank you. I wasn't gonna show this actually.